Right. It's good to be back at, it was Scala by the Bay the last time I was here. I couldn't make it the last 2 days. I had to be in London earlier this week, and I got here yesterday. So if I say anything brilliant, then I'll take credit for it. But if I say anything stupid, I'll just blame jet lag, if I may. The photos, I like to stick photos from things, places I've been and airplanes and stuff. I picked a bunch of photos of water. This happens to be in Glacier National Park, this lake here. I wrote a book that kind of summarizes what this is really about. This is one of those thin O'Reilly reports. We have them on our booth out there that we're sharing with IBM, and I'm actually going to sign copies at 12:45 if anybody wants a signed copy. If you'd rather just get a PDF, then I'll just sign your Kindle or whatever. So let's start with a little context, and I know that this is a group of people that, you guys really have been in the, chances are, being in Silicon Valley, you've been in the thick of this stuff for a while, so mostly I'll be saying things that you know, at least up front here. Probably all of you have encountered Hadoop as kind of the sort of baseline of what big data architectures are when we think about it, and it's, it originated as a batch architecture, really, where we had this problem of incredibly big data sets, bigger than anything before, and we needed a cheap, efficient way to just kind of capture it and then go back and do analytics over it. So, the typical Hadoop architecture looks something like this, where you have some big distributed file system for storage, HDFS, as it were. Tools to actually do analytics over it once you've got the data parked, and it used to be MapReduce jobs. How many of you ever wrote MapReduce jobs? Yeah, I can see the pain in your eyes. I used to rail at MapReduce because it sucked just as a programming model, and then Spark came along and it was much nicer, so that's what we all tend to use today. And when we write these jobs and submit them, then there's resource managers that figure out how to break it up into tasks. That's what yet another resource negotiator yarn is all about. And then for completeness, I added tools for getting data in and out of these clusters. So nothing that probably most of you haven't dealt with before on a very personal level. And why? So just again, setting context. Why was it good? Well, it solved the problem for the time. We just need to capture data and do batch analytics, or even more, less far back in time, even interactive analysis with like Hive SQL queries. It gave us massive, relatively cheap storage. It supported multi-user access for people to do a diverse set of workloads. And when I was doing Hadoop consulting, half the projects I did were actually replacing data warehouses. It was sort of like we'd ripped, if you look at this diagram, it's really we've ripped the database apart, whereas the database is this black box of storage and compute and whatnot. Here we've just torn it apart and said, here, you manage it. You figure out how it works. So it's kind of a rough, not as mature alternative to data warehouses, but a lot cheaper, and that's why it was popular. So why streaming? Well, even in the batch world, it actually is beneficial if you can get answers faster out of your data. My favorite example of this actually of something that in principle works just fine with batch, but actually is a competitive advantage to do streaming, is search indices, or tools like Google and so forth. Imagine that you heard about some breaking news story, and what do we all do these days? We open a browser tab and start typing, tell me about the train wreck or whatever, and expect to get like a CNN page or something like that. Well, if I was analyzing that data once an hour, let's say, to update my index, then I would be out of date by an hour, and hence I would be at a competitive disadvantage to people that do it, on the fly as things happen. So it's actually much better if we can do it quickly. This diagram is taken out of that little book, and the numbers correspond to notes that were in that booklets, but mostly what I want to do is just sort of lay out kind of the architecture that we see emerging, and then focus on the stuff on the right, which is the streaming engine parts. So obviously you have to have data, or this doesn't make any sense. And I kind of broke it up into three groups. So REST meaning like traditional, quote unquote, ways of interacting with systems where we do, submit a request for information, wait for a response, or hopefully not blocking, but often that's the way it's implemented. And one of the things I want to argue, especially towards the end, is that I think this architecture is pushing us a lot more to integrate microservices into our systems and not just have like a separate Hadoop cluster and a separate cluster for everything else. And so we'll still be doing RESTful kind of stuff, but maybe Maybe not for the data part so much as just interacting with our services, but nevertheless it can be a source of data. Mostly though, when you get to a certain scale, you're actually probably doing asynchronous analysis of stuff that's streaming in. And so I use sockets and logs to indicate, sockets being like the external stuff, like since we're in Twitter, we might as well talk about the Twitter fire hose. So if you're one of those companies that ingests the Twitter fire hose, it's not so easy to go back and ask for it again at some chunk of it if you lose it, if you forget it or something. So you'd like to, this is data that you just want to capture and store or move down the pipeline quickly and not have to go back and try to get it in some way, if you even can. And then I use logs to kind of represent everything else that might be internal, like clickstream logs, server exhaust that I might be using for operations, and so forth. So, and I mentioned clickstream logs because it may not necessarily be just operational logs. It could actually be a way of the sort of distributed logs or event stores that we use for actual business logic too. Microservices, obviously, Lightbend has its own ideas about how microservices should be done, our so-called reactive platform, but to be Switzerland here, it could be Go-based or heaven forbid Node.js or anything like whatever you like to use. For completeness, you need Zookeeper because Kafka relies on it, and other services use it for federation and storing shared information at some level. Really, the data backplane, though, is you need some sort of event store these days, something that is very good at scalable capturing of data and serving like multiple producers, multiple consumers, and Kafka has kind of emerged as the sort of de facto standard for this. So most people today are deploying Kafka in one way or another. How many of you are actually running Kafka in your environments? Probably most of you. Yeah, I figured. Okay. So here again, I'm preaching to the choir a little bit, but there's some interesting advantages to Kafka. One of which is this deliberately messy diagram where it's actually hard to reason about this architecture if I have all of these point-to-point connections, and even worse, let's say service 1 on the right here goes down, then I might have data loss from all of these sources that are writing to nothing on the other end. And how do we solve any problem in computer science? Another level of indirection. So here we go. So Kafka not only makes it look prettier, right, like that, but it gives us a unifying principle for connecting all these microservices and the resilience of everything over here could be writing data into Kafka, everything over here could be crashing and restarting, but it's okay because we've got it reliably captured and we can go back and get it when we need it and so forth. There's really 4 streaming engines I want to talk about in a minute, and actually a 5th one, which is Apache Beam. And I'll come back to those, but I'll just mention them now because I kind of start talking about them before I really describe them. And that is Flink, which you may have heard about if you got here at 9 o'clock this morning. Really interesting streaming engine at scale. Actually, the diagram's organized a little weird in a way. I'm going to talk about Flink and Spark streaming together, and I'll explain why I think those are grouped nicely together in a little bit. But then you might also have things that work more as application libraries that you embed in your microservices, like Akka streams, Kafka streams, etc. But actually, before I even talk about them, I want to talk a little bit about how you would maybe pick one for your own uses, whether you like these, which we just happen to like, or you wanted to use something else like Apex or something of that nature. But I'll come back to those in a minute. But just to complete the diagram here, these are all open source tools, and we all have standard ways of talking to them now. So you can kind of bring your own persistence to this architecture. You can use distributed file systems when that makes sense, databases, Elasticsearch, object stores like S3 and so forth. And this is pretty agnostic about where it's running too. People are doing this now in Hadoop clusters, although I personally don't think it's the right architecture for this kind of more dynamic system of things that have to run a long time with combined microservices. But you could do it in Hadoop if you want. We actually like Mesos a lot. We've been working with Mesosphere on running our stuff in Mesos DCOS. You can run it in cloud environments, Mesos on the cloud or whatever if you like, and of course Kubernetes, that isn't on the picture here. So I wrote that little booklet like 16, 18 months ago or something, and Kubernetes was just kind of out there, but not really as hot as it is right now, so things really move fast sometimes. Otherwise I'd probably have it in the list up here at the top as well. Okay, so let's go back and talk about those streaming engines a little bit. Here's a friend of mine getting sucked into the river here. So what are some of the things you were going to, like you've got to build an app. Someone told you, all right, we need to do streaming, so how am I going to decide what to pick? So let's talk about some criteria you might consider. Maybe one of the most important is, what is my latency budget? You know, how much time do I have between a datum or event arriving and when I have to get something out the other side? Well, usually we're not really talking about true real time. We use the term real time kind of, in a very loosey-goosey way in our business, but, I'm gray because I've been around a while, and in my day, the kids didn't use the word real time unless they meant it, which was, like picoseconds to microseconds, like landing stuff on barges in the middle of the ocean. But we typically don't really deal with that too much, because usually that means very customized hardware, writing in C++, and crazy stuff like kernel bypass networking and stuff like this. Really, the game here is getting everything out of the way of the signaling that I can possibly get out of the way. But mostly we tend to move into the realm of hundreds of microseconds, where we're doing like ultrasound stuff. I used to work on ultrasound machines a long, long time ago. That's why I picked this picture. Or even trading that isn't necessarily high frequency trading, but needs to be moving relatively quickly. And when you're getting into this kind of realm of latency budget, then there's a lot of actual tools in the JVM that are fast enough and are designed not to have garbage collection pauses long enough that you can actually use them. Like Akka actors could be used for this. How many of you have heard the LMAX disruptor? Okay, yeah. That was a very high-performance message queue that came out of the London finance community. A guy named Martin Thompson was involved in this, if you've heard of Martin. When you're getting into like tens of milliseconds, then you have more options. Now, the reason there's a credit card pictures here is I was once told by a guy at Deutsche Bank that if you think about someone clicking buy on a website for Amazon or whatever, there's obviously a lot of stuff that's going to happen, right? And you want to get an answer back, hopefully within a few hundred milliseconds, because that's like the usability criterion. After a few hundred milliseconds, people get antsy and they start, doing what they do. But he said that they only get 10 milliseconds of that entire, like 200 or whatever milliseconds to actually authorize the credit card. All the other overhead and transactional stuff going on just leaves them 10 milliseconds to make a decision. So obviously that's going to constrain your choices. And now you're getting into the realm, though, where tools that are designed for scaling, like Flink, can actually support this, as well as tools like Akka, Akka Streams, Kafka Streams. You do have to be a little careful when you're putting data in a queue like Kafka, because obviously it takes time to traverse the queue. So that can be a source of latency if you're not careful. And then when you start getting into hundreds of milliseconds, now you're in the realm of maybe I'm going to do more like interactive stuff, like this is like a picture of a Jupyter notebook, I think. Or I might be doing machine learning scoring, where I don't necessarily need it to be very, very fast, but reasonably fast, like looking for trends in fraud or whatever. And one of the optimizations that's been used here is microbatching. So for example, this is a technique that's used a lot in incremental machine learning trading, where rather than like update my model, which is fairly expensive to do with a per event based update, I'll just do little batches of stuff. So I get kind of economies of scale at a small scale. And as we all probably know, those of you that have been playing with these tools a lot, Spark actually started out as kind of a mini batch model as opposed to a tool for handling individual events. And as you get into larger time frames of seconds to minutes, then you have a whole lot more time to do expensive things like training neural networks or incrementally training them. Doing extract, transform, and load is here because usually you don't actually need low latency if you're just moving data from A to B. You have more time, even if it's not that expensive to do. And you can, again, use even bigger batches of stuff to get economies of scale. And I personally think if you're going above a few minutes, you should not be doing streaming at all. You should just kick off batch jobs very, very frequently. And the reason being, this actually gets to why I think microservices have become an important challenge for us data engineers, is that if you run something long enough, like you kick off a streaming job and it's going to run for, let's say, a few months, eventually you're going to see every possible problem. You're going to see network partitions, hardware failures, spikes in traffic. all kinds of things that can go wrong that you have to be able to design for. And if you come from like a Hadoop engineering background, those are the kind of problems you haven't really had to think about too much. Whereas if you come from a background of building like, let's say Twitter, the Twitter UI or other web services, those are the kind of problems you're used to dealing with. So I think that's kind of forcing a merging of thinking about these architectures. But if you can avoid that kind of long-term problem by just kicking off a batch job every now and then that just is immediately scaled for the right size it needs to be, and then it does its work and goes away, you can actually circumvent a lot of this kind of challenge. So over a few minutes, maybe if you don't need processing more frequently than that, then consider just doing batch. Okay, another criterion might be how high is the volume I'm processing. You know, if you're under, say, a few tens of thousands of events per second, well, we're kind of used to doing that with various RESTful toolkits. Not a terribly big deal. You know, when we start getting into hundreds of thousands, we can still use REST, but we have to really start thinking about using non-blocking approaches so that we don't consume resources unnecessarily and don't have things that might slow down responsiveness. But we can actually still do things on an individual basis, like complex event processing, if we really want to. When you get up into millions of events per second, then it's time to start maybe thinking about tools that actually do take your data in and immediately parallelize it over the cluster like Spark and Flink do, so that you get pretty much near infinite scalability in theory, even within tight time frames. Now, the reason I put a picture of the Nest thermostat here is it turns out Nest is written in, or at least partly implemented in Akka. And I was talking to one of their engineers once who told me that it turns out people tend to get up at about the same time every day in whatever time zone they're in. And because these things are phoning home, they get these massive spikes of traffic as all of these Nest thermostats phoned home, at about 6 or 7 in the morning every day to change the conditions to daylight, whatever people prefer during the day. And so they did all these tricks about like putting jitter in to kind of squash the peak and broaden it and so forth. But they have these, the kind of scale problems. Okay, what kind of analytics are you doing? SQL so here's something I never expected. I never expected SQL would become the scripting engine of streaming. But everybody is doing SQL now. And it's not just a fad, I don't think. You could say, well, I've got to do it because the other guys are doing it. But it actually is an extremely concise way to express a lot of the sort of data transformations we do. And if you have a UDF mechanism, a user-defined function mechanism, then okay, sure, I can plug in a hook to my business logic, something that maybe I can't just express as in SQL. I think at Flink Forward in Berlin this past spring, or whenever it was, not too long ago, there was a talk by Alibaba on how they're basically converting all of their Flink jobs to just use Flink SQL API as their kind of scripting language. So this may look familiar to many of you. If you worked with Spark, you could either write this query in just real SQL like this, or you could use like the Spark DSL that basically gives you SQL-like operators over whatever data set you're using. ETL is a really popular one, and this is, I think, a great use case for Kafka streams, for example. And it's not the only use case by any means, but for example, if I'm ingesting, say, raw logs as strings into a Kafka topic, then it'd really be nice to parse that into some nice record format for downstream consumption. So people downstream aren't all doing the same parsing and cleansing. So that's a nice way to like use Spark, or rather Kafka streams, where I'll just spin up a job that's going to watch that raw topic, parse it into some clean format, write it to a new topic, and then downstream consumers will then read that one. So obviously you have a lot of options if you're doing that. If you're doing something more complex like a data flow, then that's another case where you want a fairly rich API, and most of them now actually give you something that looks a lot like the Scala collections API like this one. This is part of the inverted index algorithm for Spark, not specific to streaming. I just happen to love this particular example. Because it really shows, like the yellow is all the function calls, and if once you get that toolbox under your belt about when do I use flat map, when do I use reduce, and so forth, then you can just string together these stepwise computations really quickly, and it's just for me it's a wonderful way to work, where I can focus on the problem and not have to think about ceremony about the APIs I'm working with. Another kind of processing, of course, might be machine learning. So here's a problem we've heard a lot of people tell us about is that, and I kind of almost hinted at this earlier, so I might be training my machine learning models, updating them periodically. Let's say every 10 minutes I want to update my spam filters, just as an example. But I need to score it with fairly low latency. So I might be using one tool for training, but a different tool for scoring. So how am I going to get models across these boundaries? And there are a lot of ways to do it, including having the same underlying libraries that are running in both contexts. But it's actually emerging as a pretty interesting challenge to make it relatively easy to update models in one sort of context of time and actually compute resources, and then actually use them in a long-running streaming process somewhere else. Actually, I was going to hide this slide because it kind of goes into detail. So obviously, I'll put these online if you want to read this, but I won't go into this now. Near the end of some of these different trade-offs, again, these are criteria to use in picking the tool you want. Sometimes you really do want to analyze each event individually, like complex event processing. And here it's usually desirable to have something that's fairly efficient on a per event basis, as opposed to something that's efficient when you aggregate over a lot of events. So if I'm doing like ETL, it fits sort of a SQL model. Maybe I don't need to look at each event individually. They're kind of anonymous in that way. They're just records. But if I'm doing this sort of a complex event processing where the routing of each event might be different depending on some criteria, then that's going to affect my tool choices. And sort of a related concept is it actually beneficial for me to have this ability to do stuff in small batches or in bulk to get some efficiencies of scale versus individual processing? And the last point would be, how do I actually want to run this stuff? So Spark and Flink, you actually start these services running in your environment, and then you submit work to them, and they figure out how to decompose that job into tasks that are going to run in the cluster. And they do a lot of stuff for you, like that scheduling of tasks, like splitting your data into partitions and all that kind of stuff. And if your model that you're trying to accomplish fits their model, then that's a really great way to work. But sometimes you actually want to do stuff in the context of microservices where you have much more control over how things are run, or how data is routed to different things, how it's all decomposed. So you might prefer something that's more of a library that you embed in your apps, and then you control all that other stuff. And the last one is, what do I want to integrate with other tools? Actually, the reason this is here is because Kafka Streams is really designed only to read and write Kafka topics, so that's its focus. But if you want something that can talk to various REST points outside Kafka or talk to databases, that might change your choices for tools. Okay, so with that list of stuff, let's talk about 4 example streaming engines and how they fit this model. And that was the stuff on the right here. The first one is Apache Beam, and this was Google's data flow that they've actually open sourced the streaming semantics part on the top, but didn't provide a runner in open source. So if you're running in Google Cloud, you get everything, but if you're running outside Google Cloud, you need to use a runner like Flink, for example. The reason I put this here, and it's the reason it's kind of indicated as a box off to the right, is Google has been thinking about streaming for a long time, and they have really thought through all of the kind of scenarios that you need to think about if you want to do streaming that's actually extremely accurate. Now, if you're just doing approximate calculations for feeding a dashboard or something, you don't need to be too careful about it. But if you want to do things like very specific accounting level, like for your accounting system kind of calculations, and not have to do it in batch later on, then you have to think about some other problems. And they've thought a lot about this semantics and are basically driving the kind of stuff everybody else is building into their streaming engines, either as an indirect way through being a runner for Beam or actually implementing in their own way things like handling event time versus system time. And just to give you an example of this, suppose for the sake of argument that I wanted to calculate exactly how many units of each product I sold in my store on a per minute basis, and I wanted this to be as close to 100% accurate as possible. Well, the problem is the speed of light is actually too slow for network systems, right? even if there's no partitions in my network, there's always going to be some events in the system that will arrive at the, let's call it the analysis node, after this 1 minute boundary. So I need to decide, okay, how long do I wait until I have got all of the data? How do I know I've actually seen all the data? What do I do, though, if I actually have like a network partition and I may not get some data from, let's say, some physical store out there for another hour? Do I do like a provisional calculation? Do I have a mechanism for sending a correction, like just maybe a retraction and then a new value? Like you might do in an accounting book, for example. So they've thought about all this kind of stuff, and they've defined semantics in Beam for expressing this kind of precision when you need it. So they're kind of driving. I think in a way Beam could be the small talk of our time. So here I'm dating myself again. Smalltalk was, back in the 80s, was this programming language that everybody talked about. It was a very influential object-oriented language, but almost nobody actually used it. Instead, we suffered through C++ and things like that, and then Java came along. Beam could be one of those tools. I actually said this in a talk recently, and somebody responded on Twitter, no, we're actually running massive Beam jobs. So I know that that's, I'm sort of exaggerating a little bit, but it could be one of these things that's more influential than actually used, is my point. But if you want to run Beam workflows, Flink is probably your best choice. Apache Apex, which I won't really talk about, is another option for running Beam workflows. It's a tool that's designed for low latency. It was written for that purpose, but also at fairly large scale volumes. And they have a new and evolving SQL dialect, if you want to program that way, and also machine learning tools that are growing. Spark streaming is probably most familiar to everybody here. And you may know that Spark actually started as a batch mode system like MapReduce. And they came up with this clever hack for doing streaming, which is, well, what if we just capture data in fixed time windows and then run a little batch job over that data? And that's the mini batch model that emerged. That is slowly going away finally. The new structured streaming library that has been in Spark now for a little while is slowly replacing the internals so that you can get down to lower latency. But if you're using the older, and even to some degree the newer library today, you're limited to about maybe half a second or a few hundred milliseconds latency. So like that credit card auth example I gave, you're not going to be able to do that with Spark streaming. But it's a great tool for training machine learning models and doing ETL and things like that where you have a little more time. And they have really rich SQL and machine learning libraries. Okay, so I kind of alluded to this. There is actually work to make Spark a runner for Beam, and there's also this sort of true streaming engine that's coming. So now let's go to libraries. So if I want to just write my own microservices but have streaming options in there, one of them is Akka Streams. If you know Akka, it's like an actor middleware system, but that's really kind of a low-level programming primitives. If I'm really thinking of data flow, then I'd like to be able to write things as, ingest data, do this transformation, join with this data set, et cetera. And that's what the Akka Streams API is designed to do. Akka itself is really good for low latency and per event processing, like if I need to do complex event processing, as opposed to like bulk aggregate kind of stuff. But it's also not designed, though, to do like sharding of your data into partitions if you have too much of it. You'd have to do that yourself. So there's a certain like upper limit of the amount of data you'd want to pass through Akka Streams without doing some engineering on your own. Whereas a Spark streaming job, or Flink for that matter, would just sort of transparently scale up with the size of your data. And Kafka Streams is kind of similar. It's also a library you embed in your application. It's very focused on Kafka, obviously. And they've done a really great job, I think, not trying to be everything to everybody, like not trying to talk to every possible data source and sink, but instead focusing on common use cases like, well, if I'm just serving a dashboard, maybe I just want to see the last value for each key, or maybe I just want to do roll-ups in my Kafka Streams app. So they've thought a lot about those kind of common use cases and have done a good job implementing them. They also recently announced exactly once. I put this in quotes because anyone who's like a purist will say you can never have exactly once in the general case. But within a wide class of assumptions, you can achieve exactly once. Effectively, what it's doing is at least once message delivery with automatic deduplication is how it really works. So it's a really nice tool for meaning you don't have to think about that kind of stuff. You can just write it, and most of the time, like to a very high percentage, you won't lose data. But once again, there's always ways you can lose data in distributed systems. Actually, this is another slide that shouldn't be here. It should be earlier. But one nice thing about Spark, though, is if you've written your application to do streaming, that you can take that business logic and easily repurpose it for batch, so that you could do both. And you could even do the Lambda architecture if you really like it. I think most people believe now the Lambda architecture is kind of going away because it has one big flaw, which is if you're using different systems for batch and streaming, then you often end up having to rewrite domain logic twice, once for each case. And it really is designed for the situation where I can only do approximate calculations in the streaming side, and I'll use the batch side to do the more definitive calculations later on once I'm sure all the data is there. We really are, as a community, trying to push this idea that we could do everything in streaming, with some exceptions, and not have to have like two systems running like this. Okay, the last bit I want to talk about is this sort of convergence that seems to be happening with microservices and fast data. This sort of sliced beef-looking rock is kind of a cool thing. It's actually in the Ansel Adams Wilderness outside of Mammoth, 1,000 Island Lake, I think it's called. So I guess the question then, okay, I put up this diagram. How does this actually relate to something like this? This is like a contrived microservice example for maybe order processing, where I'm doing the right thing by having a separate microservice for each concern, and they have their own storage, and they send messages to get services from other things. Well, I think there actually is a lot of synergy between them. First of all, from the application perspective, they really are, the best way to use them is have single responsibility applications. Whether it's a microservice that does one thing, or even the data jobs. I might be running something big like Spark and Kafka, but I tend to be focused on writing one app to do like accounting of yesterday's activity in the website, one application that's feeding the dashboard and so forth. So we can still support the same kind of design goals of like single responsibility and separate evolution and so forth. And both of them have to support data that's never going to stop arriving unless we're in really bad shape, which means we're out of business. So they have to be support all of the usual so-called reactive concepts of, resilience and scalability and durability and all that. And kind of going the other direction, anybody that starts out with like a 3-tier service architecture, if they're at all successful, eventually data will become their dominant problem. This is certainly true in this building with Twitter. They started out as the 3-tier Ruby on Rails fail whale application. And they had that Justin Bieber problem where whenever Justin Bieber tweeted something, they had to suddenly send it to, he was like the first guy to cross 1 million followers. I mean, I've been following Justin since the beginning. I'm a real fan. So, and that really forced them to decompose their architecture into microservices. And these days, of course, they just have massive data pipelines that they have to run, even though they still have a lot of small services that look more traditional. So if you came from like a Hadoop architecture world and maybe an old services world, you had some overlapping concerns, but mostly you kind of focused on different problems. And I think today it's looking more like these architectures are much more aligned together. They have to look the same. They have to solve similar problems. And they need to be more integrated. I need to get, if I have a streaming pipeline, I need to get data from other services to enrich my streams and so forth. So I think this is kind of a long-term direction for us. And of course, I think Scala is a fantastic tool for this, just to throw a bone to Scala. I showed that excerpt from a Spark inverted index example that I just love that example so much because I remember writing that in MapReduce and then writing it in Spark, and it went from here to this, and I could really think about the problem, and it's just a really good language for thinking about data flow problems in general. Okay, that's pretty much it. Just a quick shameless plug. We did release a platform recently that kind of bundles all these tools. You can tell it's commercial because this is a color diagram. marketing did this. Actually, this is, anyway. We talked about all these pieces here. And then, of course, what you do these days in a commercial open source is you provide all the production tooling around an open source core. That's pretty much what we've done. And we did actually pick DCOS from Mesosphere, which is the commercial version of Mesos, as kind of the next generation capability for managing these very diverse workloads, not just Spark jobs, but databases, microservices, et cetera. Okay, so we do have a little booth out here with IBM, and I will sign that little red book at 12:45 if you're interested. Otherwise, there's actually a link for it here. And that's it. Any questions? I did say heckle on Twitter earlier, so if anybody wants to heckle, it's a good time for that too. All right, well, I'll be around the rest of the day. Thanks a lot.